introduction. So my name is Liang Ting. I'm currently working as a research fellow at the University of Michigan. So my research recently is mainly focused on the smart battery management, and particularly here in this project, I will share with you something about how we recently designed on how we should charge our phones. So I would need to emphasize that we need batteries to power our phones or tablets, right? We need all kinds of batteries. And so let's review quickly what we have now and what we want. First of all, we want the battery to have a long lifetime. We want it to operate very well after 1 year or 2 years usage. But the truth is, the battery goes down after usage. And some, let's say, real-life data shows that in the worst case, it's an unfortunate case, the degradation could be over 50% just in 14 months. On the other hand, we always want the battery to operate longer. That means after recharging in the morning, we want it to survive our daily usage. But the problem is, these phones, these toys, hardly survive 1 day single usage. And on the other hand, we want these things to operate reliably. So this is a little tricky, but let me show you an example. If you're using iPhone, and if you're using iPhone 6s, then maybe you heard that last year Apple has a program to replace the iPhone 6s battery for free. And the reason for that is because some phones are reported by the user to say, okay, my phone shut off entirely, I still have 30% remaining power. That means this number, this 30% or 20%, somehow is not reliable. And last but not least, that we wanted to operate safely. And we mentioned that we have a lot of battery problems, fires, explosions on phones. Okay, so in this case, we need batteries, but in reality, the batteries are far from perfect. There's a long way to go. And here, particularly in this project, I should show you our attempt or exploration to try to, let's say, slow down the battery degradation a bit and thus improve its lifetime. So, what is battery degradation? So, for any battery, if you look inside of it, you can see any battery can be specified by the so-called design pattern. That's some number marked outside the battery. But when we actually use it in real life, we always cannot always fully use its capacity. Because inside the battery there is an active component, the current is right in the figure. And this inactive part actually increases over usage. And this is called battery degradation, and because it's increased, the battery capacity that can be effectively stored inside is reduced after using, after 1 year or worse after 2 years. So is this a problem for phones? So to show this, let's say how users actually reflect about this thing, we did a user study about 150 participants. So asked them, what do you care about this degradation? And about 90% of them, they said, okay, I really noticed that my phone operates shorter after, let's say, half a year or 1 year. And about 70% of them, they think, okay, this is a bad thing, which somehow we want to be addressed. And even many of them, they also said, okay, I may like you to switch to a new phone just within 1 or 2 years. But still, if you can slow down this thing, it will be good. But the fact is, the battery degradation actually is something nature. We cannot actually stop it. But actually, the case is how fast the battery degrades. Actually depends on how we use it. And particularly here, they will show that how we charge the phone, how we charge the battery actually affects the battery degradation. And with the existing potential charger inside the phone already, if we don't use it properly, it can accelerate the thing. So let's review what's inside the phone, how we charge the phone inside the phone. In principle, most of the existing chargers follow this principle called constant voltage and then constant current and then constant voltage charging. It's a two-phase charger. So in this principle, what we do is actually, when we charge a battery, we first charge it with a large and constant current. And because it's a large constant current, the battery voltage will increase faster, and the SOC, the remaining power inside the battery, will increase automatically. And this phase stops when the battery voltage reaches the maximum value. For example, in our phones normally use 4.4 volts. And then at that point of time, the charge will switch to the constant voltage charge. That means during the second phase, instead of control the current, we use the voltage to charge the battery. It's a constant level. And because we are doing this, the resultant charging current will be gradually reduced. And because this thing, smaller charging current, the SOC on the remaining power will increase, so much slower than the first phase. And when the charging current reduces to a very small level, I cut off here, then we say, okay, my battery is fully charged 100%. So in this case, you can see first phase constant current charging fast, and it's called CC charge for short. And in the second phase, we give voltage as a function now. It's constant voltage and CV charge for short. And another thing is, all the charging process, actually there are three numbers made there, voltage and current. Okay. So from this thing, we can observe some basic facts here. The first one is, all these three numbers actually are already embedded in the driver in full. So it's often a planned charging process. And faster at the beginning of the charging, and then goes to slower because of the CV charge. So why? We just don't always use a quick charge, but with a high charge rate. The first reason is, okay, if at the second phase we don't stop the charge rate, we don't reduce it, it's very likely the battery got overheated and exploded. And another reason is, this CV charge, although in terms of charging rate, it's slower, but it actually helps the battery health, or it reduces the battery degradation. So let me show you this with some numbers. What we did is, we have a battery testing device. We can use it, we can control the charging, discharging, logging all the detailed process during the experiment. And what we did is two sets of measurements. In the first set, we use the fully charged. First go with CC charge quick one, and then go to CV charge slower. And then we complete this charge battery, this is called 1 second. And then we repeat it for 1 per second. And then in the second set, we don't use CV charge at all. We try always to charge with the high power ones. And then we also repeat it for 1 per second. So we see, okay, after this 1 per second environment, how much degradation we achieve. The results show the different battery is, if we just skip the CV charge, the degradation will be much significant, much larger than they always ensure there is a full utilization of CV charge. So why this is the case? But let's go back to the CCCV charge. That's because during the CV charging phase, again, we use a much smaller charging current. And this smaller charging current, when we use it to charge the battery, that means the chemical reaction inside the battery, okay, it's not that intensive. Okay, it's mild, it's very gentle. And this is good for battery health in many different aspects. And so as a general concept is, this CV charge phase helps the battery health is because it somehow allows the battery to rest or to relax a little bit after a high power charging phase. Okay, this is some physical and chemistry fact of the battery. And so let's summarize the existing design. In state-of charging solution, we go with use offline charge plan profile. We go with faster and slower, and we go slower because we need this CV charge phase to slow down the degradation. But how we actually use it in our real life. So to show this, we collect about 1,000 charging cases from 7 users. And then we see, okay, how the user check their phones. From this about 1,000 charging cases, we find that about 40%, 50% of them actually last shorter than 2 hours. Okay, that means if we have, depends on the specific phone model we use, it's very likely this phone is not fully charged within just 2 hours. If this is the case, let's see another example. We check the end of this charge SOC. That means when the user disconnects the charger from the phone, what is the number showing on the phone screen? And then we find that about 60% of the charging is actually terminated before the phone is fully charged. And if you look at it closer, that's to say, there's a magic number of 80% SOC. That's actually the rough number when the charging switch from constant current to constant voltage. And if you treat the 80% as magic, then you see there is about 40% charging terminated without using CV charging at all. So that means when we use the phone, we often early terminate the charging. And then because of this, whatever design already inside the code, that means we missed the CV charge phase. And we cannot relax battery, and then we accelerate battery degradation, somehow unnecessary. So to address this thing, what we designed is a relaxation over our charging algorithm, or let's say our working shop. The principle is very simple. Still, we want to charge as quick as possible, but we want to ensure there's enough relaxation. And we want the charging to be finished within the user's available charging time, say 1 hour or even 10 to 15 minutes. The idea is just like this. When you charge the battery, according to existing design, there is a maximum voltage and it can turn on. And once the battery voltage reaches to this maximum voltage, we can switch to the slower phase of CV charging. But the case is, when we actually use it, we may not have enough time to fully charge it. We only have limited charging time. So the algorithm wants to be sure the charging phase actually stops within this available time. So what we did is actually just lower the index. Okay? So in that case, the charging will turn into the second phase once this VCC is reached. So early, but still this helps, but may not fully address the problem because let's say the CV phase itself may be our problem. So if we want to make it shorter, or we make it shorter, that's when we introduce another voltage here from VCB. That means during the CV phase, we charge it with this even smaller voltage to make it this CV charge phase shorter. So in this case, we can see this arc of that still is a two-phase one. First it goes to quick charging and slower charging. And the difference is actually we make the CV charge phase, we check it earlier, and then we try to make it shorter. So in this way, we achieve a customized charge based on the user's real-time time. I can only charge with 1 hour for this point. And so as you can see, the technical challenge actually is to define or to identify optimal control parameters. For example, the voltage value here, and actually there are another two current values in the charging process. But these details are just needed. So another thing is, it is our compatible to the existing charging that's hardware of phones. The other is used. So why? So this figure shows this existing circuit design of the charger. So it can supply either a constant current or either a constant voltage. And which one we use is depending on the battery voltage. If the voltage is small, then we use constant current. That's the first case. And if the voltage is high, then we use the voltage as the charging control. So this is what happens with current. And everything needed for our is just okay. Actually, we don't need a ladder to change this, right? But it's still use this ICC, whatever inside the core. And for this voltage, currently it's just like a fixed value, but we want it to first supply the value and then change it to another one. And for the decision of which one to trigger, actually, even the similar things, it's still based on whether the battery voltage is high enough, and but it's different value, that means that's enough. So in this case, you can see our version requires additional hardware support, and all we need to do is to change these parameters inside. But can we do that? Actually, yes. It's because in this charger drivers, they already provide such interface. We can just put this function and then run into the values. So that will also to the charger driver interface. And then evaluation, so what we did is take case studies. We provide 8 of them. Each of them we charge and discharge the battery for 1 per second, and then we see how much degradation. So the results show across the 8 shows about, let's say, on average, it's about 40% degradation slowdown achieved in this hour. And the last thing is, okay, we have two solutions now. Existing charging solution and a new one. The existing one is faster, but the rate also faster. And the new one is charged slower, but it has more battery health. So how do we divide it? It's from the user. So we ask the user to, let's say, whenever charging the phone, to tell us how much time we can charge, and then which charging method we want to choose. As a summary, so here we tackle this degradation problem. We want to slow down the increase in the red part. And the observation is existing design are good for battery, but the missing consideration of user behaviors. Combine these two, actually there is some unnecessary degradation. And so to address this problem, we came up with a new charging, let's say, algorithm called charger. We try to keep the battery at a healthier state for a long time. So just briefly about the future work is in this project, what we did is we explored relaxation to maintain battery health for a longer time. And you just mentioned actually there are many other problems for batteries, for example, operation time, reliability, and safety. Actually, if we can properly explore this relaxation or the rest of the battery, we can address all of these problems. So that's all I have for today, and I'll be here and I'm glad to answer any questions. Thank you.